Okay everybody, today's lesson is called Force of Friction, and we're going to break this lesson up over a couple of days to make it as easy as possible for you, because it tends to be a slightly long lesson. And actually on this page it says rough preliminary notes. Let's go even more rough than that. Let me take you back to the work that you just finished a couple of days ago before the quiz. Remember, we left off with questions like this. An object like a rocket is traveling up into the air, and it has an applied force that's provided by engine power or muscle power. And that's not the only force. There's always a force of gravity acting in the downward direction because of the Earth. And when you take the difference between these two forces, you end up with the real overall net force. So imagine taking this same situation, but now let's turn it sideways and lay it on the ground. So instead of a rocket being fired up into the air, let's take a look at something like this. A 50 kilogram mass that's sitting flat on the ground, and it's being pushed. So there's an applied force, and that's muscle power or engine power. And that's forcing the object across the ground. But now, just like the rocket, there's a force holding it back. But in this case, it's not because of gravity, it's because of this. It's because of the fact that it's sitting on the ground and it's dragging as it's going across the ground. That's called force of friction. And again, use a capital F, but in the lower right-hand corner, put another variable, in this case a lowercase f, for friction. But same type of idea as the rocket question. We're going to have masses that are being forced forward with some kind of an applied force. We're going to calculate how much friction there is on the object and take that off of it. And in the end, that will give us a net force, just like it did for the rocket type questions. But now in this case, it's laying flat on the ground. Where's gravity? Well, there is still a force of gravity on this mass. If this 50 kilogram mass is sitting on the ground, there is still a force of gravity. But that's in a completely different direction. And when things are sitting on the ground, they can't move down into the ground. The ground itself actually pushes up on the object with another kind of force. So now it's getting a little complicated here. There's so many different forces on this diagram. But when you have objects that are being forced into surfaces, the surface itself pushes back on the object with the last force that we're going to be dealing with in grade 11. It's called a normal force. Again, write a capital F and put a capital N in the lower right hand corner. These are the four forces that we deal with in most of the grade 11 situations. Now, force of gravity and the normal force, they have the exact same value, because when something's sitting flat on the ground, take my calculator here for example, when something's sitting flat on the ground, it doesn't move into the ground and it doesn't move up into the air. So the whole point of these two forces here, the normal force cancels out the force of gravity, and it's not in the situation. So back to the diagram the way it was before, you still have an applied force where you're pushing something, and you still have friction coming off of it because of dragging it across the surface, and that's still going to give you an overall net force, but gravity and the normal force will cancel each other out. Now, one little point of confusion, and I'll change pen colors here. Normal force and net force, they both have an N. They both start with an N. That's why I've been writing net force as a full word on all these lessons, a little NET in the lower right hand corner. You might not have been. You might have been just writing an FN for net force. So one thing I want you to do is either pause this video or remember afterwards, go back through your notes from the last couple days before you even start the rest of this video. And anytime you see that you wrote F with a little N in the lower right hand corner, change it to net. You haven't done anything with a normal force yet. And you have to make sure not to confuse these two, because grade 11 students in the past have, and it leads to all kinds of problems later on. So every time you have a net force, write the word net. And then when you have normal force, if you use just an N, you'll remember the difference between the two. So just to fill in the the bottom of this page, some little brief notes here. When does one encounter a force of friction? And I'll make these notes as short as possible. Well, that's whenever you have two surfaces in contact. There's no such thing as a frictionless connection between surfaces. Whenever you have surfaces in contact. We don't have any frictionless surfaces. I mean, some people think maybe ice would be frictionless, but imagine a hockey puck traveling across ice. If ice was frictionless, the puck would just go forever. So even ice has friction. In what direction does the force of friction always face? This is one force that we always know the direction. It always opposes motion. When you know which direction an object is moving, friction is always completely backwards. And finally, what is the formula for force of friction? Well, here's where it's going to be a little bit different. I'll write it big so that you can copy it a little bit larger. Capital F with a lowercase f for friction equals, this is the very first time, and it might be the very first time in math and science, that we're going to start introducing letters from a different alphabet. So the very first variable in the force of friction formula looks like this. It almost looks like a capital U, but it's got this funny little tail on the front of it. That's a Greek symbol. More on that in a second, but that's the very first variable, and you multiply that by normal force, not net force. So here is your force of friction formula, and it's going to be the exact same formula this entire year, and even in grade 12 it's exactly the same formula. To get your force of friction, you have to multiply the coefficient of friction. You take your coefficient of friction and you multiply by your normal force. And we're going to do some examples to clarify all this, don't worry. But what you need to know for now is coefficient of friction. These are values that you look up. Every single connection between every single type of surface has been tested and tested and tested for decades, for a century and a half. And you find those values in charts like the one on the next page. So these are, you can see right at the top here, coefficients of kinetic and static friction. That squiggly looking U in the formula, you get them off charts like this. So you look and see what type of materials you have in contact. For example, you can see the first one is rubber on concrete, dry. So if you have a piece of rubber and it's sitting on a piece of concrete and it's dry, your coefficient of friction can be found in this chart. There's a range on this one, so we'll probably not use those ones. But you just need to know that you get coefficients of friction off of charts if you need them, or they're just given in questions. And up at the top here, what are some more details I should know about coefficient of friction? Well, first of all, they're unitless. They're not meters per second, anything like that. They're just unitless values. They describe, and I want to use the word friction here, but I can't because you use coefficients to find friction. So I'll say they describe the, let's say the stickiness, I guess. Describes the stickiness between materials. So if you have a higher coefficient of friction, it means that you have a stickier connection between the materials and therefore a greater force of friction. And the third point, if you just kind of look on this chart really quickly below, you can always recognize the coefficient of friction because they range from 0 to 1. There are very, very rare instances where they actually go above 1, but not in this course. They range from 0 to 1, and they're usually decimal places. So again, in this chart, you'll see all these 0.6, 0.18, 0.78. These are numbers that are reference numbers that you look up when you need them in a question. Now, the only thing that's confused some students in this class in the past when it comes to coefficients of friction are there are two types. There's a coefficient of friction with a little tiny s after it, and a coefficient of friction with a little tiny k after it. The s stands for static, and the k stands for kinetic. What does this mean? Well, there is a very slight difference how sticky something is on a surface when it's sitting at rest. You've all experienced this before. When you go to push something, if it's sitting still, it's a little bit more sticky than it is once you get it moving. So for example, if you look at here, steel on steel, if you're doing a question where you're moving a piece of steel across a steel surface, you'll notice that when the piece of steel is sitting there and it's not moving, when it's static, the coefficient of friction is 0.78. But as soon as you get it moving and it's sliding along on its own, and it's still steel on steel, but it's not sitting still anymore, the coefficient of friction drops to 0.42, and that's kinetic friction. You don't usually have to choose between these columns, but every once in a while you get a question where you might get a slightly wrong answer, and this is going to be why. But more on that later. The easiest thing to do right now is to do a couple of examples, because I'm sure you're just absolutely confused, and examples usually make things a little bit easier. So let's do one together. In this question, you've got a 50 kilogram piece of steel, and it's being pushed along a steel surface. This is right in the description. 50 kilogram piece of steel being pushed across a dry steel surface with an applied force of 520 newtons. So let me just draw this on here. It doesn't say which direction, so I'll just randomly choose to the left. So there is a force. It's an applied force. You're actually pushing it. So that's muscle power. You're pushing it with 520 newtons. The question here says, what will be the actual forward acceleration of the piece of steel? Well, there's only one way to get acceleration. Acceleration equals net force divided by mass. So the mass is there, but 520 is not the net force. So this is where we're going to go at the end of the question. We're going to solve for the acceleration using a 3-step calculation and get an answer. But this is going to be probably step 4 or even 5. I'm going to number it as step 5. Let's start with some other steps first, because we need to solve for the net force. And if you go back to the diagram, here's what's happening. You have an applied force forward, but because there's two surfaces in contact here, not like one of the rocket questions from last day, there's a force of friction holding it back. The steel is dragging along a steel surface, and we need to figure out what that force of friction is so that we can get a real net force here. The formula for force of friction, there's only one. It's coefficient multiplied by normal force. The coefficient, you're going to go back to your charts. This is a steel on steel question, and the steel is dry. So if you look on the chart, steel on steel dry has a coefficient of friction of 0.78. Let's use that. 0.78. So we need to multiply by the normal force. Now here's where it's going to get confusing just this one time. Where do you get normal force from? Well, normal force is the surface pushing up on the mass. This is normal force. And what you need to know in grade 11 is there is no formula for normal force. You can't calculate a normal force. The way you get normal force is you look in the up and down direction and see what the value of the normal force has to be by looking at other forces found in the up and down direction. Well, there is another force in the downward direction, gravity. So in order for this question to work and remain flat on the ground, normal force has to cancel with force of gravity. So here's step 1. You need to work out the force of gravity. And this is why we had a lesson last week on force of gravity. Force of gravity is mg. So I know this seems like it's getting very complicated, but you'd be surprised. Sometimes the more complicated questions get, the more sensible they end up being in the end, because you see how the whole situation works. So here's what we do. We're going to calculate a force of gravity. Mass is 50. G is 9.8 meters per second squared. That comes out to 49. No decimals. So there's step one. Calculate your force of gravity because you're going to need it. Step two. Determine the normal force. Well, it's only grade 11. And in the up and down direction, you're only going to have one force. Gravity's down, 49 newtons. Normal force has to be 49 newtons. Think about this. That's the only way it could work, is if these cancel each other out. So they have to be the same value. Step number 3. Calculate your force of friction. Friction is coefficient times normal force. So 0.78 multiplied by the normal force, 49 newtons. Now this one I need a calculator for. 49 times 0.78. 38.22 newtons. So that's just the force of friction. So if I can simplify this diagram a little bit more, because I've written all over it now, this is what we actually have. You really have just this. You have a forward force of 520, and you have a force holding it back of 38.22. No formulas involved here. The net force is going to be the difference between these two. Or if you really needed to write a formula, net force would be whatever the applied force forward is minus friction. So 520 newtons minus 38.22. And we don't want to round anything yet because we're not at the end of the question. So I'll keep all my decimal places. That's 481.8 newtons. So that's your net force. Now, finally, since you figured out your net force, you can end this question off with this calculation that's been waiting up here as step number 5. You can calculate acceleration if you take net force and divide by the mass, 50 kilograms. For a final answer, and now you can round it if you want, because here at the very, very end, this is going to give an acceleration of 9.64 meters per second squared as a final answer. This is a big mess. This is why I tell you guys too to number your steps. I forgot one. Step 1, 2, 3. I guess this would be step 4. And then finally step 5 to finish this off. Now, step number 5 is solving for an acceleration. We can go back now and take that acceleration and go back to all the work we were doing before. So these questions really do kind of snowball. Let's do another example. All right, this time there's a 20 kilogram mass. It says a 20 kilogram rectangle made of rubber is being forced forward across the surface of a road by an applied force of 400. So let me write that on there. Applied force 400 newtons. However, the actual acceleration of the object is measured to be 17.5 meters per second squared. Can't really label an acceleration on here, but I'll do it like this, I suppose, a little squiggly line maybe, just to remember that the acceleration is 17.5 meters per second squared. That's it. That's all the information you're given, and it says calculate all this stuff. Calculate the force of friction, calculate the coefficient, and then part C asks you about the road, what it's made out of. So how do you start this question? How do you calculate force of friction when you're not given any other information? Well, we're going to start backwards in this question because the acceleration is 17.5 meters per second squared. And net force is mass times acceleration. It's just usually you don't know the acceleration, so you don't usually start with net force. But in this case, we're going to work backwards. The mass in this question is 20, and the acceleration was given right at the start as 17.5. So you can begin this question by solving for the net force, 350. So think about this. You're pushing the box forward with a 400 Newton force. It's only actually moving forward with a net force of 350. So even just without doing any math, those two numbers are so easy, you can probably surmise just from that the force holding this box back has to be 50. However, I don't want to do that without a calculation. So let's write down calculation number 2. Net force. You always take your applied force, whatever it is, and you subtract off friction. So if you know your net force is 350, and you know your applied force is 400, you can solve for force of friction. Oh, I'm sorry, I was off the screen there. Net force always equals applied force minus friction. So if you know the net force is 350 in the end, and you knew that you started with an applied force of 400, you can rearrange this formula, although mathematically you probably don't need to. But you can rearrange the formula and you'll get 50 as an answer. So friction in this question is definitely 50 newtons. So that's part A, done. Calculate the force of friction. Here's the force of friction. Part B says, what's the coefficient of friction? Well, there's only one formula that has coefficient in it, and that's the force of friction formula. Force of friction equals coefficient times normal force. This is the only place that you can calculate a force of friction if you're not given it, so you have to rearrange this. Coefficient of friction, I'm going to take the normal force and bring it to the other side. That's force of friction divided by normal force. Well, we already have our force of friction. That's 50. What about our normal force? How do you get that? Well, again, you cannot calculate a normal force with a formula. You have to look at the diagram and you have to say, normal force is this. Normal force is the ground pushing up on the mass. And in grade 11, it's always going to equal whatever the force down is. And that force down is force of gravity. So, once again, we have to calculate force of gravity. Here's step 3. Calculate your force of gravity. I've not left myself very much room here, partly because I'm writing with this big fat black marker. Force of gravity is mg. The mass in this question is 20. G is 9.8. I'm running out of room, so I'm not going to write the units on that. Multiply those together, and the force of gravity is 196 newtons. So there is no formula for normal force, but you need to transfer that value and say the normal force is 196 as well. So take that value and let's return to this calculation here for part B. Force of friction is 50. Normal force is 196. Units cancel. Divide those two numbers. And your coefficient of friction is 0.26. Now, this value actually makes sense if you think about it, because coefficients of friction are always between 0 and 1. So that looks like a coefficient of friction. And then part C in this question, there's no math to be done in part C. It says, is the road made of concrete or asphalt? Well, you can use this. You can use coefficients of friction to identify materials if you have to, but you'll have to look back at a coefficient of friction chart like this one. And I've written all over this right now, but it did say in the beginning the box was made of rubber. So if you look at the top of this chart, there's actually 4 entries for if you have a material made out of rubber. And there's 4 different surfaces that it would be dragging across. If you look at the kinetic friction for all these surfaces, they don't even go as low as 0.26. The first one ranges from 0.6 to 0.8, so it can't possibly be rubber on concrete, dry or wet. Even the wet value for concrete starts at 0.45. So of these 4 possibilities here, the only one that could actually work with our answer of 0.26 is this last range here. So it could be that the piece of rubber is on wet asphalt. It can't even be dry asphalt because it starts at 0.5. But it could be in this range right here. So part C of the question would be, and it's just a word answer, rubber on asphalt, but it would have to be wet. Okay, there's 4 practice questions. I'm sorry that this video was a little bit longer, but actually the reason it's longer is because I'm trying to go slower and make it a little easier. There's 4 practice questions. The first 2 are very, very easy. Question 3 is a little bit longer, but I broke it into 3 parts, and each part is a very easy calculation. And then question 4 is very much like question 3 actually, but it's not broken into parts. It's just a word problem that gets you to go through everything. Try these questions out. The answers are in bold, but I will post full solutions so that you can check your work line by line. And that's it for right now. So focus on these 4 questions, and we'll continue with force of friction next day.